It's a pleasure to welcome everybody to the second public lecture of the trimester. The speaker tonight is Andrea Cavagna, and the title of this public lecture is The Seventh Starling, The Wonders of Collective Animal Behavior.
Thank you. Okay, so thank you for coming. I think this is the most embarrassing situation in my life. I was told that this was a public lecture with people knowing nothing about science, yeah, this is okay. Well, I come here and I understand that I discovered this was at the margin of a workshop in spin glasses packed with theoretical physicists. So I propose Pierluigi to switch talks, so to give a real technical talk. He said no, because even though perhaps no one of the public is in the audience, the public will click on my talk later. So, you know, they are asking me to give a very, very elementary talk in front of a very, very qualified audience. So it doesn't come.
That now this audience has just heard you.
Yeah.
Saying that.
So let me ask, is there anybody in the audience who's not professionally trained as a scientist? Oh, two. Okay, good. So I would like to ask to everybody else to leave, please, and can just stay here, cozy, the three of us. So if you were a general public, I would be supposed to apologize for my French, that, as you hear, sounds awfully a lot like English. But given that you are all scientists, that is not going to be a problem, I guess. And let me also thank warmly the organizers for inviting me here to do this public lecture. So all this will be really very elementary, I hope. So I'm going to talk about collective behavior. We have a sample here. These are starlings. A tourneau, as I discovered from the French translation of my title, over the skies in Rome. So starlings spend most of the year in the northeast of Europe, and then during the winter they migrate south, and many of them spend the winter in Rome. During the day they stay in the countryside to feed. There is not enough food in the city center. However, for the night they come back to the city center, probably because it's warmer. Nobody knows for sure. And but before settling down on the trees, they do these wonderful evolutions, which is called flocking. So people have been fascinated by this kind of behavior for a very long time. We all think that the first who has been asking reasonable questions about this phenomenon was Pliny the Elder, the Latin natural philosopher. This is a classic comment you do in a public lecture while scientists don't give a damn about these kind of things. Anyway, and the basic question he was asking was why? Why do they do that? And in this he fully qualified as a biologist, because the why is typically the question of biology. And after more than 2,000 years, I would say that we still know very little about the why, especially in the case of bird flocks. Sometimes you hear that they do this because this is an anti-predatory behavior. So they do this to dodge the attack of the predator, which in a way is true, because by sticking together they dilute the risk, because they're constantly under the threat of the peregrine falcon. You will see later in the images the falcon attacking. However, this also doesn't make any sense, because if they just stayed on the trees without doing any flocking at all, the falcon would not prey on them. So why they do that, it's completely unknown at the moment. There is another set of questions, which is the how. How they do that. So how do they keep this extraordinary cohesion, this amazing response to external perturbations? And the how is typically the question asked by physicists with their reductionist approach. So how do they do that? Of course, the two questions are connected. And you can hope, at least this is the physicist hope, that once you understand the how, so once you understand what are the elementary behavioral rules giving rise to this, then you have a better chance to understand why they do that. Okay. Collective behavior is not certainly restricted to birds, and we find that it crosses many, many scales, both length and time. So these are, for example, bacterial colonies. So from the very small, we find collective behavior there. You have collective behavior in insects. So these are huge swarms of midges over Lake Victoria in Africa. This is a picture I particularly like. These are all the trajectories of malaria mosquitoes in our lab. So you can have collective behavior, which is also relevant to understand what is going on with malaria, because in the case of insects, these swarms are typically a mating contest. So are very important for mating, and in the case of malaria, it's very important to understand how that happens, of course, to try to fight malaria. So we are trying to get data on this. It goes on also for social insects. These are bees, but also for fish. This is a school of fish, and even mammals. These are herds of sheep. And of course, surprisingly, as it may seem, for a very long time, people have been developing theories and models about collective behavior virtually in absence of real experimental data. So it was a fantastic situation for doing science in this field, because you could formulate any model, any theory, and there was basically no experimental test to compare your model and theory with. So it was very good. Not entirely within the scientific paradigm, however, it was fun. This went on not at the times of Pliny the Elder, but kind of up to 20 years ago, 10 years ago. And then, well, why that happened was not that clear, because that was already the time where we could, make particle accelerators and so on, but not getting the data on moving animals in 3 dimensions was considered to be very hard. Then there have been an evolution of technology, digital technology, and other things. So in the last couple of years, we finally have some data, and I would say that the biggest contribution of what my group have done has been to produce hard data to compare models and theories with. So let me give you a short glimpse of how do you do experiments in this field. So how do you produce the positions of each individual bird in time? So the principle we use is the one of stereometry, which is the same that your eyes and your brain use to distinguish 3-dimensional positions. So you have two or more different visions of the same object at the same instant of time. Public lecture, so no details here, but the only important point is that by the fact that the two images hit the two sensors at different position, you can reconstruct the 3-dimensional position of your object. The only important point here to understand is that the resolution of your system, so how good you are in locating the object in 3 dimensions, is proportional to the distance between the two eyes. So for example, we have our eyes at only a couple of centimeters, so we can only resolve 3-dimensionally at a couple of meters. But clearly we will be looking at birds, typically from a roof in the city center of Rome, so birds will be at hundreds of meters from our cameras. So we need a very large baseline, a very large distance between the two eyes. And if you do the math and if you ask what is the resolution that you need, you see that you need cameras at about 25 meters one from each other. And also we use more than 2 cameras for, let's say, technical reason, to have more information. So this puts some very nasty constraints on where you can actually run your experiment, because you have a very sparse equipment with all your cameras 25 meters one from each other. And so you have to find a public building who is willing to host you for setting up all this apparatus. And fortunately, we found the Museum of Roman History at the center of Rome, who has been hosting us for a couple of years now. So you have all your cameras there, and then you take your images. And then you have to start another part, which is the computer vision. So this is, for example, a small flock. And we have recognized each individual bird. But you see that sometimes birds are so close to each other that they form a blob. So it's very difficult to distinguish them. So the idea is that they can form occlusions, optical occlusions. So they can go on top of each other on one camera, not on the other camera, though. So the first problem you have is how to resolve these occlusions. Well, fortunately, what happens is that once you form an occlusion in one camera, like that, those two birds, they do not form an occlusion in another camera because of parallax. So if you see them on top of each other from one view, you are able to distinguish them from another view. So what you have to do is to exploit this extra information of all your cameras to reconstruct and track the individual birds. And this is what we so I do have a rather technical slide, fortunately. And this is what we do in the following way. So when birds form what we call the virus, so an occlusion, the problem you have is that you have two objects, so two birds, but actually you have four paths. And you don't know who is who at the end of the virus. So you could take it wrong. You can say that the blue guy goes into the occlusion and then ends in the green guy. So in that case, you made a mistake. However, you have the other camera where the two guys do not form an occlusion, and you have to exploit that. By the way, if they form an occlusion in all cameras, this means that they really went on top of each other in 3 dimensions. So if they do that, we don't want to know why they did that, but for us, it's just the same bird, okay? So it doesn't matter. So if they do that, fine. We are happy to, confuse them, no problem. However, if they're not exactly on the same point in 3-dimensional space, then at least in one of our cameras, they should be separated. Okay, what we do here is that basically we assign scores or probabilities. So we form big matrices. In this case, it's a small matrix, but in the real case, it's a big matrix. And here we have the 4 possible paths there. 2 are right and 2 are wrong. And here we have only 2 paths. And by using some rather complicated geometrical constraints because of the different position of the different cameras, we can assign probabilities to these pairs of trajectories. And then we optimize the whole matrix, meaning that we find the global pairing of all trajectories, which gives the higher probability, and those are our trajectories. So basically, we reduce the whole problem to an optimization problem, and half of the people in this audience works in optimization, so they know about that. So the important point I'm making here is that we use the information from all the cameras to resolve these ambiguities due to occlusions. And once you do that, then you have practically solved the problem. So that, for example, is the 3-dimensional reconstruction of that particular flock there. This wiggling of the birds, this zigzag of the birds is because of their wing flap. Okay, so they're not going in a straight line because they're constantly doing like that because of the wing flap. Okay, so now you have your data after a couple of years of work. And what are you going to do about that? So the question we first asked was, what kind of interaction is ruling this behavior? So interaction means a direct exchange of information. So clearly, they're not moving randomly. Otherwise, they would crash into each other. There would be no cohesion at all. So what kind of exchange of information? How does it work? How they can keep track of each other in order to produce that behavior? So in physics, to measure forces, Typically, you take different particles. Oh, hi. Another non-general public element. Hi, Florent. So, so you measure forces between particles. So, for example, to understand something about the electrostatic force, what Coulomb did was to put two charges at a certain distance and to measure the force, right? And then he worked out the dependence of this force on the distance. And then once you have this microscopic description of your force, so you really have the law telling you how the force decays with the distance, then you can hope to be able to say something at the macroscopic level. So you know about the microscopic level, and you want to do calculation and to understand how the hairs of the child go up when it goes on the slide. Okay, this kind of program that we use in physics is problematic in biology, and especially in the case of birds, because you see, it doesn't make any sense to put the two birds on the perch and measure the force. I mean, this is not clear what you are going to do. Also because these are not real forces, of course. This is why people call them social forces. These are forces heavily mediated by their brain. It's just a way they react to each other's actions. Okay, so you cannot do the same kind of experiment as Coulomb. And another point is that even though you were able to do that, so imagine that you are able to measure the force between two birds by this kind of reductionist experiments, or then between three birds or three fish and so on. Well, the problem that you do have in biology, in my opinion, is that you cannot scale up to the full flock. Meaning that once you know the behavior, the mutual behavior, for example, let's say that you study two birds in the wind tunnel. Now you know how do they keep track of each other, how do they react to each other's positions, and so on. How do you know that they keep the same behavior in a flock of 1,000 starlings, of 10,000 starlings? So paradoxically, this, which is what you would do in physics, because then you can, in physics you can just add linearly forces, is what has typically been done, well, is done by biologists. But actually, I, as a physicist, disagree with that. I think that you have no guarantee that the behavior of two guys alone is the same that they would have in a very large crowd. We cannot exclude that, but you cannot know that that is true a priori. Think about humans, for example. Would you say that your behavior when you're chatting with someone as a pair is the same as when you are in a huge crowd getting out, I don't know, in a panic from a stadium? Perhaps yes, but perhaps not. So our point is that, especially in biology, you need to study the phenomenon at the collective level. There are emergent phenomena at the collective level that can hardly be envisaged when you study just a macroscopic system, so a couple of individuals. So the situation in biology is somewhat reverse with respect to physics. So in physics, now we have quite a clear understanding, for example, in condensed matter about the microscopic interaction. And we're devoting all our effort in understanding how those microscopic interactions create a certain behavior at the macroscopic level. In biology, we go the other way around. We observe the macroscopic phenomenon as quantitatively as we can, and from that we try to infer what are the microscopic interactions. So it's inference. So we go from the macroscopic to the microscopic. Of course, hopefully, when we've done that, we will be able to do some prediction about other phenomena that we are not observing. So in the case of birds, the way we applied that at the beginning was to try to study the structure of the neighbors of each bird, and from that to try to infer something about the interaction. Okay, what happens in a flock is that typically the nearest neighbor to a bird, so the bird nearest to each given bird, is on its side. So it's neither in front nor in the back. So there is an anisotropy in the distribution of the neighbors. Okay, so you're flying, you select the nearest guy to you, and you ask, where is it? Okay, typically it's not in front nor in your back, but it's on your side. So this is a map, if you want, of the sky, of the sphere around each bird. Okay, so the bird is at the center of that map. So front is the center of the map, and the back are the two sides of the map. And this is the probability density of finding your nearest neighbor. So dark means low probability. So you see, you typically do not find your neighbor in front or the back of you, but on their side. So because of that, we clearly understand that there must be some interaction between the birds. We knew that, but this is a proof, because otherwise, if they were just randomly moving with no interaction, they would be just randomly disposed all over the sphere. So there would be no structure. Well, we do find the structure. So there must be interaction, which is good. And what is interesting is that if you do the same now, not for the bird which is closest to you, but for some faraway bird from your 10th nearest neighbor, so some guy who is down there, and you look at their distribution in space, well, in that case, you do not find any structure. You just find fluctuations. So this means that guys around you, guys around everybody, are structured in some way, anisotropic. However, this structure decays with the distance. And clearly, this must be the effect of the fact that the very interaction between the birds decays with the distance. So this is expected. Interaction and structure decays with the distance. And this is very natural. Even in physics, all fundamental forces decay with the distance. Okay? For example, in the nucleus, there is a competition between the electrostatic force and the strong nuclear force. And then you find a balance. But the important point is that everything depends on the distance. And what is even more important, that this distance, you see here, is measured in meters. So it's the normal physical metric distance. So forces in physics depends on the metric distance. I say metric, but normally you just call it distance. Okay? Now, surprisingly, biologists, when they developed their first models, but even physicists, they just took the same kind of rule. They said, well, clearly there is some tendency to align to each other, so the interaction will be an alignment interaction because we don't want to crash into each other. And we want to stay together without crashing, so an alignment interaction. And what we say, okay, let's say that then every guy interacts with all other birds within a given radius of interaction. That was a metric radius, just like in physics. So the force was decaying with the metric distance, which made sense. However, how do we know? How do we know that birds have the same notion of distance as we have in physics? It could be, but perhaps it's not like that. So to answer this question, what we did was to measure in ways you don't want to know about, but basically by using statistical inference, maximum entropy for the connoisseur. Anyway, we measure the strength of interaction in many different flocks. So in this rather confusing graph, forget about everything apart from this red dot. So each panel is a different flock. Real flocks, no simulations, so real data. Okay? So the inset is just a semi-log representation of the same data, and the blue line is the step function approximating that. Forget about that. So the important point is that what we plot here, J, is the strength of interaction as a function of the distance in unit of neighbors. So 5 means the 5th nearest neighbor, 10th is the 10th nearest neighbor, and so on. So it's the interaction as a function of distance. And what you see, as expected, is that interaction decays with the distance. However, what kind of distance we have on the assise here? It's not meters, it's unit of birds. So 1 is my nearest neighbor, 2 is the second nearest neighbor, and so on. So what is striking about this plot is that all panels have the same scale of the distance. So I was able to reproduce all these 6 flocks, and actually we have many more. We have this kind of data for now, I think, up to 20 different flocks, using for all of them the same scale of this distance n. Now, as I told you, this distance is not a metric distance. It's not meters, it's unit of birds. So it's what we call the topological distance. And now, why it is surprising that I could use also always the same scale? Because, as you've seen very clearly at the beginning in the video, flocks, they have all different densities. So the mutual physical distance between birds changes very much from flock to flock. So if the interaction was based on a metric distance, you wouldn't expect to be able to do that. While here what you see is that the decay rate in unit of birds, not in unit of meters, is always the same. And if you measure it, if you fit it with an exponential, what you get is more or less 7. So this brings us to the title. So this is the pictorial situation. The scale of the interaction, what is constant in all systems here, is not the metric interaction range, which depends on the density, but it is a topological interaction range. They're always interacting with the same number of birds, irrespective of their distance. And this is very uncommon in physics. In physics, you would have that this dotted circle is the same. So then, in this case, you would interact with very few birds. In that case, you would interact with very many birds. Well, this is not what happens in flocks. In flocks, you fix the number of interacting guys, not the number of meters within which you interact. Yes?
Is there any evidence that those birds can count until 10 or 20?
I'll come to that in a minute. So topological distance is very uncommon in physics, as I told you. However, it's very common outside physics. For example, sorry, public lecture again. In the case of the metro, when you take the metro, you do not measure distances in meters, but in number of stops. Okay, so that is an obvious topological version of distance. And there are many other cases in the social sciences where what matters is not the physical distance, but the topological distance. Now, why do they use this notion of distance? Why do they use this kind of interaction? Well, if you think about it, the reason is obvious, and it's to keep a large cohesion. So they're constantly under the pressure of the predator. And have you seen in the images, they swirl, they change density and shape continuously. Now, imagine that they have a metric interaction. If you have a metric interaction, once you drop outside the metric interaction range, you cannot interact anymore. So you evaporate. This is exactly why particles evaporate. Okay? If a fluctuation brings you far enough from your group, then it's done. You're out. And when you're out by yourself alone, it's very probable that the falcon will eat you rather than a guy in the flock. So getting astray is not a very good thing to do, and a metric interaction would cause that very much. However, in a topological interaction, when you change your density, you're always interacting with your neighbors, because this is an interaction which is scale invariant, if you want. It doesn't depend on the density. So in this case, keeping cohesion is much easier. Okay? And if you do simulations, and you can do that, you can simulate a model which is exactly the same, but for one different, that in one case the model interact with a metric interaction, in the other case with a topological one, and you do this kind of experiment. So you send a falcon, meaning that you do a perturbation on the flock. What you find is that in the metric case, you have many stragglers, many isolated birds after the crash, while in the topological case, you don't. So it seems clear to us that the reason why these biological systems have developed a topological interaction is that, evolutionarily speaking, a higher cohesion is much better. Then, why 7, coming to your question? Well, the real answer, we have no idea. But let me speculate here. So the fact that they interact with 7 neighbors, does this mean that they can count up to 7? Well, not really. So there is a whole scale of numeric abilities in animals. So from pre-numeric to numeric, and this has been studied quite a lot. So there is a phase in which you do not count, but you estimate numbers by drawing patterns. For example, you see a triangle, it's a tree, and so on. So they did this kind of experiment for birds. Those were pigeons, not starlings. And the experiment was the following. They were presenting to the pigeon, you see, two different sides of food, one with 3 grains and the other one with 4 grains. So with different numbers of grains. And they trained the pigeon to pick up the grain from the plate with the largest number of grains. So they trained the pigeon to distinguish numbers. What they found is that, so if they couldn't distinguish, it would be 50-50. Okay? If they can distinguish, it's larger than that. So what they found is that beyond 6 and 7, it's very hard for the pigeon to distinguish the two numbers. So you can distinguish 3 from 4, 4 from 5, but 10 from 9, not really. No matter how severely you punish the pigeon to train him, no way for him to distinguish. Okay? So this could be the reason why we find a 7. So it could be a cognitive limit. Okay? Of course, this is not the only answer. Another possibility is that this number optimizes something. We really don't know. And yeah, this is one of the most open problems for us. At the beginning, we thought it was really something related to some cognitive limit, but now I think we have other ideas. So we don't know. We don't really know. This is the only evidence we have.
For humans, unless we really count one by one, probably there is a similar limit.
Yes. Indeed, also humans use this prenumeric ability, which is called subbatizing. So for small numbers, we do not count. We estimate by looking at the pattern. Beyond a certain number, we start to count. It's very hard to do the experiment with humans because the crossover between non-counting and counting is very smooth, while birds do not count. So after a certain threshold, you clearly see that they get confused. But again, it could be something different. And even in humans, keeping track of 7, 6 guys is hard enough even for us, right? So even if you can count out to 1,000. So perhaps it's not related to counting at all. So summary up to now, birds interact with about 7 neighbors. This is a topological interaction, not a metric one. By the way, interesting enough, all models developed before this experimental finding of ours were using a metric interaction, not a topological one, and now things are changing. And this mechanism grants a strong cohesion. But what about collective response? So what about how the whole flock dodges the attack of the falcon? You've seen that at the beginning, right? So 7 neighbors is a very, very short-range interaction. So 7 is less than the number of birds you have around you, directly around you, at short distance. In the sense that in 3 dimensions, so in 2 dimensions is about 6, the number of neighbors. In 3 dimensions would be something like 15. So 7 is a small number. So these are flocks of 10,000, 100,000 birds. So an important point is that the interaction is short range. So how do they respond collectively so swiftly to external perturbation? And this brings us to the second concept of today, which is correlation. So correlation is something connected but different from interaction. And I deeply apologize about this slide with all these physicists and scientists in the audience, but I need to explain what correlation is to the very few non-professionally trained scientists in the audience. So correlation is a way to indirectly transfer information. So the best example, in my opinion, is the phone game. So everybody whispers a message in the ear of the neighbor, okay, and the message travels. And at some point, the message gets so much corrupted that you cannot understand anymore the message. So in this example, the important point is that there are 2 scales of length. The first one is your interaction range. In this case, is 1. You're only speaking to one person at a time, the one directly at your side. Okay? This would be the 7 from Starling. But then there is another scale, which is how far the information travels before getting corrupted. And that is what is called the correlation length in physics. So it's the spatial span of the correlation. So you see, correlation means that you can have the same behavior even though you're not directly connected to each other. You're not talking to each other directly. Okay? So the point is that clearly the correlation length cannot be smaller than interaction range. It must be at least of the same order. Okay? But the important thing is it can be larger. So you can transfer information for much longer distances than the one you directly interact over. So what we did was to measure the span of the correlation in real flocks. In particular, we measure how the change of direction of one bird here is correlated to the change of direction of another bird in another position. And we did that for every possible distance in the flock. So how much correlated are the birds at short distance, medium distance, and large distance? Okay? This is what we found. This is for two different flocks again, so each panel is a different flock. So the red curve is what you saw before, is the interaction, is the strength of interaction. And you see on this scale, which is crazy, the x-axis here is again the distance, the topological distance. But now instead of going from 0 to 10, it goes from 0 to 1,000. So on this scale, you see the interaction decays very, very, very rapidly. So as we knew, it's a short-range interaction. What is interesting is the blue line. The blue line is the strength of the correlation, is the correlation line. So how far the correlation propagates. So you see that is much more long-range than the interaction. So even though they only talk to their 7 nearest neighbor, this simple mechanism is able to propagate information very, very far, much beyond 7 neighbors. And this is something which is well known in physics, that you can create correlation with a span much larger than interaction. But let me go back to the example of the phone game. So imagine that you're very, very good in playing the game, that we play the game here in this audience, and that you find that you can transfer the information up to, I don't know, 30 people. And after that, it gets corrupted. I strongly doubt that we will be able to do that. However, let's say that this is what happens. So you have a correlation length of 30, which is much larger than 1, so you're doing good. And imagine that here we are 50, something like that. So 30 over 50 is kind of good. You have propagated your information to something like 60% of the system, 70% of the system. It's fine. So now let's assume that other 100 people comes, because the lecture is exciting, and so another 100 people arrives, and you play the game again. What you expect is that you still get information through 30 people. Nothing's going to change. Why having more people in the audience would change your correlation length, right? Doesn't make any sense. So now you're still propagating the information up to 30 people. But now the total audience is, I don't know, 200, which is not that good, perhaps. And then other 200 people arrive, and you're always propagating of 30 people. So when you are 1,000, you're always doing 30 people, so it's not very good after all, because you do not propagate information to the entire system.
These are correlations between velocities of two birds.
Between velocity fluctuations.
So somehow vectors and
Yes, it's correlation between...
Same time.
Yeah, same time. Sorry, yeah. In all my metaphors, I'm mixing time and space. But in reality, we're doing this at equal times. And these are the connected correlation of the velocities. That is the correlation of the velocity fluctuations with respect to the mean.
Doesn't it take time for the information to propagate in the flock?
Yes, yes. That.
I would expect that you jump by, let's say, like 7, like at the 1,000 furthest, well, 20 jumps.
Yes, of course, there is both space and time. And I could speak about the way information travels in time. That is another work we have done recently. But for the moment, let's just say that if the information gets corrupted and it cannot arrive to the 15th neighbor, I mean, no matter what is the time, I mean, it doesn't arrive there at all. Okay? So we're just talking about static correlation length here. But of course, then you have to study the full space and time problem. Okay? But the two things are connected. In general, the two things are connected. So going back to my example, so you do not expect in normal system that the correlation length, so the span of the correlation, depends on the system size. Okay? Well, but this is not what happens in flocks. In flocks, what you find is that the size of the correlated regions scale linearly with the system size. So you get a flock, you measure the correlation length, which is quite large. Now you get a flock of double the size of the first one. The correlation length is double the size of the first one. So it's like they're playing phone game, and every time some new people arrive, the range they reach increases. So the range of the correlation increases with the size of the system, which is what is called in physics a scale-free behavior. So there is no real scale. The only scale is the size of the system. So what they are doing is that they are basically propagating information. Well, they're transferring information to the whole flock. So now, if the flock doubles in size, they propagate it to the double length as before. Okay? So scale-free correlations, yes?
You measure the flock size in number of birds or in size?
You can do both, and in this case, what is plotted here is meters. It's really meters, okay?
Could you repeat? This case is what?
Meters. Meters, yes. So, yeah, exactly. This was one, before we found that, we said, okay, let's measure the correlation length. We found before that the interaction is topological, so what would be the correlation length? Will it be topological or metric? But then, so the question was overridden by the fact that actually it was scale-free. So it was scaling with the size of the system, okay? So a scale-free correlation is something normally quite peculiar. In physics, you have to have some condition to have a scale-free correlation. And it means that basically each bird in the flock strongly influences all other birds in the flock. So what the biologists call the correlation length is effective perception range. And you can understand why. So it's not the actual perception range. The actual perception range is these 7 guys, but the effective perception range is how far the correlation spreads. So you can imagine that in this condition, really the response of the flock is very, very good. Because now a falcon arrives on this side, I change my behavioral state, okay, and this change is felt by all the rest of the system. Of course, technically, I should explain to you how this propagates in time, and I can do that later privately if you want. But the important point is that really the correlation is as large as the entire flock. So how this happened? Well, I don't think we still have a final answer, but let me mention to you one of the possibilities, which is a fiercely debated possibility. The idea is the following. In physics, you have this kind of behavior, this kind of scale-free correlations, only when you locate the system in a very specific and peculiar point of the parameter space. So, for example, when you have a system, a magnetic system at its critical point, at its critical temperature, then you achieve that. So, by this I'm meaning that normally a typical physical system is not scale-free. So, in order to be scale-free, you have to tune something, to put the system in that specific situation. So, one possibility, one hypothesis is that because long-range correlations are useful to the system, useful to do what, however? Yes, to respond, but it should be quantified better. But let's say because long-range correlations are very useful, because collective response is very useful, then evolution has put the system exactly close at that particular point where you do have scale-free correlation. So this would mean that evolution has driven the system to some kind of critical point. Now, it is important for you to understand that this is still an hypothesis, and it's fiercely debated. And there could be other reasons why we find these long-range correlations. And so this is a very much open problem. However, from the experimental point of view, what we find, not only in birds now, but we find evidence of that even in swarms, and other people have found evidence of that in bacteria, is that spatial correlations are very, very strong in many of these systems. Okay, so it seems there must be a very fundamental reason why that happens.
Especially if you are non-equilibrium, very often you don't have to find it. So
yes.
Only sort of special solid state sort of equilibrium type form.
Yes, yes, yes. Thank you for the question. So let me go a bit technical for 1 minute. So there was a beautiful paper by Greenstein and co-workers in the 80s when there was a craze of the self-organized criticality saying exactly that. If you have the following ingredients, which are normally quite easy to have. So out of equilibrium dynamics, so you violate the tail balance, and you have a conservation law, then you create long-range correlations generically. Yes. So I think this is exactly what we should be careful about in these cases. However, what is discussed in this paper is exactly that you do need a conservation law. So the conservation law is essential because what gives you... Yeah, well, I agree with you. So for example, we do find conservation law in this case of other quantities, which I can discuss with you later. But in this particular case of what is surprising, the scale-free correlation surprising here, we didn't find any real underlying conservation law. But this is exactly why one should be careful. If you are out of equilibrium and you have conservation laws, you can create long-range correlation just generically. Yes, so thank you for pointing that out.
The number of birds is conserved, and this is not enough.
Yes, the number of birds is conserved, even though not always in our data, actually never in our data, because we never able to reconstruct 100% of the bird each instant of time. However, yeah, I don't see how that would create long-range correlation of the speed, for example. But yes, there may be conserved quantities. I mean, the important point is that conserved quantities should be connected to the correlation function that you are measuring. But yes, number of birds is conserved. Yes?
When you say long-range correlation, you think like something like power law correlation, or because in physics you can have power law correlation in phases, not just at the critical point. Maybe you are thinking to more strong long-range correlation.
Okay. First of all, we find long-range correlation of different degrees of freedom. For some of these degrees of freedom is kind of obvious. For others, it's not. For example, we find correlation, long-range correlation of the orientations. That is a soft degree of freedom, so it's a continuous symmetry. The system is in a broken symmetry state. So if you stretch the Goldstone theorem a little bit and you want to apply it to birds, you would expect to have long-range correlation of the direction of motions. So that, in a way, is not surprising, and it doesn't say anything about criticality. So in this respect, I agree with you. However, we find the long-range correlations also of the modulus of the velocity, of the speed. So even when you have spontaneous symmetry breaking of a continuous symmetry, okay, that would be the massive mode. So that would be the mode which is not supposed to be long range. Okay? So we also find that to be long range correlated, to be scale free. Okay? So that was more surprising. Swarms. As you will see in a minute, swarms are in a disordered state, so they do not break a continuous symmetry. So in that case, again, so you are above the Mexican hat transition. So in that case, again, you would expect a massive particle, two massive particles. But in that case, again, we find long-range correlations. Okay. So yeah, sometimes it just seems to be due to the math, like Goldstone theorem kind of arguments. In other cases, it is either something related to the off-equilibrium phenomena or some closeness to some critical point. But you see, I didn't even mention that in the slides. I just gave you the empirical Okay, final part of the talk. Is correlation a consequence of order? Okay, you all know that the answer is not. Okay, fine, but for the few people, the public people in the audience, in biology, typically the idea was that collective behavior means order. That you have collective behavior if you have that all the individuals in the groups are doing the same thing, which is clearly what is going on in a flock. They're all flying in the same direction. They're all turning in the same way. So there was also the idea that perhaps even this correlation, this big correlation that you find in these kind of systems, was due to the fact that you have order. Okay? So the idea was, okay, in that case, you have a very strongly aligned flock, so you have order, you have collective behavior, and here you will also have a strong correlation. While here, for some reasons, I don't know why, you have chaos. You have no order, no collective behavior, no information transfer, nothing. So these are all ways to say the same thing, that you have collective behavior, order, coherence, coordination, correlation, all the same thing. Okay, is that so? Our answer is no. So look at this system here. This is a swarm of midges, small mosquitoes, in a park in Rome. Villa Paganini, by the way. This is the guy, is Dasilea. It's a small, nasty bastards that sometimes they bite you, sometimes they don't. So clearly here you see no order at all, right? So you would say, well, no collective behavior here. And you could argue, well, no, they're all staying in the same position. So there must be some collective behavior, otherwise they would just evaporate and go around. But what you discover when you start studying midges is that they all stay on top of what is called a marker, a landmark. So for example, this would be an excellent marker for a swarm. So you put this here, and then midges go up on the sheet of paper and they form the swarm. So much so that then you can, by slowly moving your marker, move the swarm and bring it in front of your cameras. Okay? And this is exactly what we do. For example, this is how we got this kind of data. So you see, this is a swarm, a real swarm. That is a three-dimensional reconstruction of the same swarm. And we can physically carry around the swarm by moving the marker. So then you say, haha, so you see no collective behavior. They're just staying around the marker, like mosquitoes do around the lamp. So what proof do you have that there is collective behavior here? Clearly there is no order. You just told me they just hang around the marker. So why you go studying this system? And I had this question asked by some colleague in biology. You're wasting your time. You will find nothing there. Fortunately, for all the wasted time, it was not like that, because look at this. So these are two swarms. One, it's a real swarm. It's a three-dimensional reconstruction of a real swarm, no simulation. The other one, it's a random swarm, meaning that it's a simulation of a bunch of random walkers, of random moving points, confined to stay in a given region. So these are n random walkers in an harmonic potential. Same number, okay? So you see, first reaction here, yes, they are just exactly the same. This is what I told you. There is no collective behavior. Because, of course, a bunch of random walkers hanging around a marker is not what our intuition would call collective behavior. However, if you check it more closely, after a while, at least some people do see which of the two is the real swarm and which one is the artificial swarm. Not always for the right reason. Some people get it because one of the two has less spatial fluctuation and the other one is more spatial fluctuation. But the right reason is that the natural swarm, sometimes you see that some midges fly together for a while and then they get apart. And sometimes there are more than two, okay? So you see by eye, but it's difficult, that there are some correlations perhaps. Okay, by the way, I guess that by this time you have understood that this is the natural swarm and this is the random one. They have correlations. However, measuring correlation by eyes is very hard. Okay, it's much harder than measuring order by eye. You know, detecting whether the system is ordered or not is easy. Detecting whether it's correlated or not, less easy. So we can measure that. So this is a plot for exactly those two swarms that I showed you. Okay. So the red line is what you get for the non-interacting case. So zero correlation, as you should. These are non-interacting particles. The black line is the correlation for the real swarm. So you see a very non-zero correlation. Okay? By the way, this is the interaction range, which incidentally, in midges, is metric. It's not topological. But this is another story. But this is the interaction range, and this is the span of the correlation, which is quite larger than the interaction range. Again, okay? So our message here, which is really trivial, I mean, for physicists, but perhaps was not so trivial in biology, that you can have correlation even in absence of order. And the idea would be that when you have an ordered phase, okay, it's typically because you have an order in transition. So by changing some parameter, noise, density, whatever, you can bring your system from an ordered phase to a disordered phase. So on this axis here, so this blue line is the amount of order you have. And you can go backward. You can go from a disordered phase to the ordered phase. Okay, so this is what happens, for example, in a ferromagnet or in the Vic-Check model. But the important point we wanted to make, which you know very well, is that the amount of correlation peaks around the transition. So you can have correlation even in the disordered phase. So midges seems to live here, swarm seems to live here, while flocks, in a way, because it is a continuous symmetry, seems to live here. So they are very different, they look very different. One is highly ordered, the other one is highly disordered, but they're both strongly correlated. So we would argue that, and this, going back to the beginning, would be our best definition of collective behavior. We would argue that correlation, not order, is the true hallmark of collective behavior. And once you have established that, then you can start studying other systems with this in mind. So this is what we are doing now. So these are stem cells. And you grow a colony starting from just one cell. So the colony grows. Okay? And you see, if you run the movie, you don't see much order. However, now you know better. Perhaps you still have collective behavior because you perhaps have correlations, even though you do not have very obviously any ordered phase here. So our message was just use the tools of statistical physics, correlation, connected correlation, to detect when you do and when you don't have collective behavior in a system. And this is what we are doing right now for this system. Okay, that was it. Thank you for your attention.
Questions, comments, curiosities?
Yes, at some point you had pictures where you were measuring against topological distance in certain interactions, right? So is it something that you get out of a statistical method?
Yes.
Say, well, it's some interaction in a sense that you don't specify what the origin is, but it's something that would be what a physical system would have if it would have the behavior that you see in your flock?
Yes, what we did was to use maximum entropy methods. So let me go back to the slide. Okay. Yes, this is it. So, oh, sorry. Yes. So in maximum entropy, what you do is that you measure something. In this case, what we measure was the correlation function of the velocities, the connected correlation function. And then you build the minimal probability distribution compatible with that experimental observable. This is one possible method of inference. So in this case, the blue line is the experimental input. So this is the experimental input. It's just measured from the data. And then you feed the blue line into maximum entropy. And maximum entropy spits out the red line. So, by the way, I think that this is quite nice because sometimes maximum entropy is criticized by saying that you get out what you put in. Okay? But in this case, I would like to emphasize the economy of maximum entropy. So this is the amount of correlation you feed the method. But a method understands that you can simply have this interaction, so set into 0 all these coupling constants to reproduce a long-range correlation. So in this sense, it's smart enough not to give you a long-range correlation, but to give you a short-range correlation, even though you're, sorry, not to give you a long-range interaction, but it gives a short-range interaction, even though your correlation was long-range. The first time we discovered the topological interaction, though we didn't use maximum entropy. What we measured that structure of neighbors, which I described at the beginning, and even in that case, we found that the structure decays with the topological distance and not the metric one. And the estimate of the radius is the same. So now we have two, I would say, rather independent methods by which we estimated that.
I was wondering, do you have models of these interactions that you can implement in a computer and sort of reproduce this swarm behavior?
Reproduce this?
This behavior.
Yes, it's full of models. No, I didn't. I don't do models. Well, I do sometimes, I have to be honest. But I think that the field is overcrowded with models, in my opinion, and theories. Well, yes, there are good models. The problem is that sometimes they're too good. So when you have a model with 50 parameters, it looks wonderful. It's actually so wonderful, it's as good as the real birds. So then you should study the model exactly as you study the real birds. It's very difficult to then understand in that case what is changing what. So this is why we try to stick to the data as much as possible and to try to work out general laws directly from the data. But yes, it's full of models out there. But whatever I show you today, apart from those random midges, which is not actually a model, it's random walkers, all I showed you today was real data. But yes, it's full of models out there.
Francesco first, and then I have two questions. The first is whether it is sure that there is a two-dimensional structure in the Borgi clock. And also the second, from the fact that the density of the clock cannot be too low, density I mean per cubic meter, cannot be too low, there should be metric content in it.
Yes. So let me answer the second question first. So the second question is, okay, you told me that the interaction is topological, so that whatever is the distance, they always interact with the nearest neighbor. But that is certainly going to be false. Because if the interaction is visual, which is most likely, at some points I'm not seeing anybody else. So yes, there certainly is a metric cutoff. Yes, there must be a metric cutoff. There is a large distance metric cutoff, and also there is a short distance metric cutoff. And we find a clear indication of the body size in the data. So if we feed the distribution with hard spheres, we fit the hard sphere radius in exactly the wingspan. So while on the other hand, we do not find evidence of the metric cutoff in the data, but probably simply because they do not probe those densities. But certainly there is a metric cutoff there. Now, regarding the first question, two-dimensional structure, I don't think I mentioned that no, well, I don't think, well, perhaps not in previous talks by me. I don't think I have never mentioned this in any of my talks. Let's say that was something that we thought was there in the very preliminary data some kind of 10 years ago. So what is true is that they have an aspect, so flocks have an aspect ratio which is not spherical, fine. So typically they have one dimension which is a bit shorter than the other two. However, it's far from being two-dimensional. It's not two-dimensional at all. But it's a kind of uneven aspect ratio, okay? But it's not as flat as this Mac. It's more, and by the way, they change their shape so frequently it is hard to even make a statement. But at that time, we're desperate for results. So we may have said that at some talks. But it was from private conversation, I guess.
I come back to this idea that there may be some critical regime there. So two questions. First, do you believe that? Second, what are the parameters? So, evolution may have put the parameters. What are the parameters apart from density?
Okay, I would like to skip the believe question. And let's go to the parameter. So I've described here two systems. Let me focus on midges that are perhaps, well, in my opinion, they're clearer for what concerns this question. I have, yes, this is something I didn't show you, but is important. So the order in transition in midges is ruled by density. So the control parameter is density, which was a well-known control parameter for the Vic-Check model. So at fixed amount of noise, not too large, of course, if you change density, you can induce order. So at very low density, remember, this is a metric interaction. So simply, very low density, they never interact with each other, so it's disorder. When you increase the density, they start interacting, okay? At some critical density, you have a phase transition to an ordered phase. So now, imagine that instead of density, you plot nearest neighbor distance here, okay, which is the same thing. So here you have a disordered phase, and here you have an ordered phase, okay? So this is a realistic setup, because you can imagine that the amount of noise is always the same for midges, but their density is not the same. Why? We don't know, but we have data of swarms with different densities. Okay. So then you have a phase transition going on in density. This would be the bulk phase transition, okay? However, you have system with finite size. And this is what we put the emphasis on lately. So if you have a very small swarm, you know that if you plot the susceptibility of a very small system, well, not much happens around the phase transition. Okay, so the phase transition gets a bump which is sharper the larger the system. But not only that, the position of the peaks changes with the size of the system. Okay? So what we do find is that swarms of different sizes really seems to, let's say, surf this line, meaning that the larger is the size, okay? Look at this plot. If you take a larger size, you need to be closer to the critical point to be close to the peak. So if you are really critical, what you should have at finite size is that your control parameter should depend on the size. So larger swarm should have a smaller nearest neighbor distance. And this is indeed what we find in swarms. Okay? So I would say this is the most explicit indication of that. We are not saying that the system is here. Even because in finite size system, to be exact at the critical point doesn't mean anything. I mean, you're below, effectively below the critical point. You're ordered, while they are not ordered. So if you're claiming that there is some criticality going on, you should find some scaling between the control parameter and the size, which is what we find in midges. In birds, the situation is more problematic because we don't have a clear idea what is the control parameter. The degree of freedom which seems to be critical there is the speed. So they have long-range correlation of the speed. So the idea is the following. They certainly have a natural physiological speed, which is about, I don't know, I think it's 12 meters per second. But they can go a little bit faster, a little bit slower. So in their equation of motion, you put all the interacting part. I want to interact, but then you need to put some confining potential for the speed, because you cannot let it go to 1,000 meters per second, even less than 0, right? Because they would fall down. So you have this harmonic potential now constraining your speed. Okay, so the coupling constant of this harmonic potential, you see, the lower it is, so the flatter is the harmonic potential, the more long-range correlated would be the speed. And this is what we find even there. Whether I believe that in general you have this or that, I still think that we need more data. I just describe what we find in the data.
Can I rephrase your question in a way you might find palatable to answer?
I did answer to that. I found that palatable.
The belief one. So you said that it was fiercely debated, this assumption of criticality. So can you give arguments of the opponents?
Yes, the argument of the opponents, I think, is the one the gentleman mentioned before.
Okay.
That in general, you have cases in which you are very far from any critical point, and you have long-range correlation because you violate the tail balance and you have some conservation laws.
So it's never arguments based on the way you analyze the data? Because in financial markets, there's also this debate about long-range correlations. And there's a huge debate about the fact whether this comes from heterogeneity or long-range correlations. Because if you have a very heterogeneous system, you can think that it has long-range correlations where you're just matching together very different subsystems.
Okay, 2 points you raise. Heterogeneities, no, we went through that. I was very worried about that. Phase separation, you don't have that. So that we are pretty sure. Analysis of the data, yes, risk. So whenever you say that you have a system which is close to the critical point, after you have run some inference procedure, for example, maximum entropy, then you have to be very careful. Why? Because we know that there are shortcomings there, technical shortcomings. So for example, if your sampling is not good enough, you may run into troubles. However, what I show you today was directly from the data. I did not calculate the correlation function going through some inference procedure. Okay? I actually calculated the interaction range, but I'm not claiming that the system is perhaps close to critical point because of the interaction range. I just look at the data and I look at the correlation function. This is why I think that the most important and relevant objection is the one of the gentleman before. Because here, even for midges, we are not running any inference, any maximum entropy. We're seeing where are they in this phase diagram, if you want. So the problem is really whether there is another mechanism of equilibrium mechanism generating this correlation. In the case, I am always very worried. I mean, not worried because I didn't write anything wrong up to now, but that there may be something different. But what was striking for me was to find this finite size scaling in midges, because that is not something you would expect by these off-equilibrium arguments. It's really something which is so much like critical phenomena. But perhaps it's wrong. I mean, we still need much more data to...
One last question. Yes, it's related to this finite size scaling that you found. So if you take two swarms and you put them together...
Which we can't.
Okay, but...
Gedanken experiment. Fine, I like it.
Experiment. So one thing is they separate, they don't want to be together, or they stay together, but then they have to adjust their density, right?
Yes.
If they adjust their density, then it cannot be evolution. I mean,
it cannot be?
Evolution that decided.
No, right. Okay, good point. Good point. Okay, I said before, to simplify, that evolution has driven the system to criticality. Wrong. What I meant is the following, that evolution may have driven the system to some construction, such that the system is then dynamically able to self-tune to criticality, which is even more entangled. So the idea is, as you said, that the system, especially because of finite size scaling, has to decide what is the right density then and there. However, what about this? Let me give you an alternative view.
They don't stay together.
Okay, exactly. So let me give an alternative view. imagine now that their control parameter is what it is. It's this point here. It's 0.5. They do not tune it. That day, because of the temperature of the wind, the light, they decide that that is their density. Okay? And then you start to build up the swarm now. So you have 2 guys, 3 guys, 5, 10. So now you change n at fixed control parameter. We always think about changing the control parameters at fixed n. But now you do the opposite. You change n at fixed control parameter. So then you're climbing up this thing here, okay? So at some point, so you see, at some point, so at the first you build correlation, but at some point you find yourself out of the peak of the correlation. So given some value of the control parameter, you have an optimal n. So from this curve you see the optimal value of the control parameter given n, but it's also true the opposite. Given the control parameter, you have an optimal n. So once you arrive at that optimal n, what happens if you start adding midges? Perhaps the swarm will break down. So is this criticality or not? So then depends on the point of view. It's kind of anthropomorphic. It would be very nice to do the experiment, but these are experiments done in the field. But this would be a kind of different interpretation of criticality in biological systems.
So, if there are no other questions, we thank the public.